today we are going to continue and finish the fundamentals. You may already know a concept in previous courses. For example, when you design a linear amplifier, you claim the gain equals 20 dB. What does that mean?
dB. Decimal.
Yeah. dB. 20 dB means how large is the gain, is the amplification factor. 20 dB. How exactly? For example, if the input, the amplitude equals 1, how large is the output?
I don't know the conversion.
That's a conversion, right? Alright. So today we are going to discuss about this dB. dB is defined as an operator applied to a ratio. So the gain is the ratio. The gain is the output divided by the input. For example, if the ratio is in terms of the ratio of power, P2 over P1, then we take the log of this base 10, then we times 10, that is called dB. D means deci, so means 10. Because this unit is too large, this number is too large, so that's why I multiply by 10 to make the unit smaller. So this is dB equals this. This is for power. Sometimes the input and the output are represented with the voltage. The input voltage equals 1 volt, the output voltage equals what? Right? In that case, if we use a V2 over V1, then we are going to use still take the log of base 10 then times 20. If the ratio is in voltage or in current, so current 2 divided by current 1. The reason is because the power is proportional to V squared over R, right? And R we assume is constant, so that is just proportional to V squared. So we plug this one into here. So log log P2 over P1 equals log P2 V2 squared over log V1 squared, or both base 10. Then we can move this one is log V2 over log V1, then that's square here, and multiply by 10 here, and this one is 10, this one is 10. Then we move this 10 to here, so that's why it equals 20 log base 10 V2 over V1. So every time we mention if the ratio is in terms of power, then multiply by 10. If in terms of voltage or in current, then this same thing, power is also proportional to the current squared. So we need to multiply by 20. Keep this in mind, don't make a mistake. So now, if we say the gain equals 20 dB in terms of power, so how large is the gain in a real value, not in dB? What's the factor? 20 dB equals here, so equals 100, right? So if the power gain equals 20 dB, that means the output power divided by the input power equals 100. 100 times larger. Make sense? How about if it says the voltage gain equals 20 dB? Then voltage gain equals 20 dB, so 20, so this ratio will be equals 10. So log 10 base 10 equals 1 times 20 equals 20 dB. So that depends on what we are talking about. If we're talking about ratio of power, then 20 dB equals 100. If we are talking about voltage or current, then 20 dB, that will be equals just 10. Don't be confused with this. Next one, we discuss another unit. It's called dB W, dB watt. When we mention a power, so the power equals 1 watt. We already know this. I can claim that the power also equals 0 dB watt. These two are the same thing. So what does this dB watt mean? dB watt means how many dBs compared to 1 watt. So the base is 1 watt, then you compare your power with this one, then convert this ratio into a dB. So 1 watt equals 0 dB watt. And because 1 watt divided by 1 watt equals 1, then log 1 equals 0, 0 times 10 equals 0. Okay. Now let's do another one. How about 0.1 dB watt? How large is this power? Keep in mind 0 dB here, 0.1 equals 10, right? Then times the log base 10 and this power divided by 1 watt. We are looking for this power, the absolute value, how many watt. This one, your power compared to 1 watt, this is the ratio. Then take the log, convert it into a dB. Okay, that one equals 0.1. That is given. So here this one divided by this one. So this one will be log base 10. This thing power here 1 watt equals move this one to this side, so that's 0.01, and this one to here, so that means this one equals 10 to the power of 0.1, then times 1 watt. You need to use a calculator to calculate what is the power to the of 0.01 to the 10, then give us some value, then times this. Alright? Make sense? So dB watt means how many dB is compared to compared with 1 watt. That is 0 dB watt equals 1 watt. This again, this unit is large, so the next one will be use a milliwatt. That means this one is the dB value compared to 1 milliwatt. Now look at this. 0 dB watt equals how many dB milliwatt? I want you to fill this blank. 0 dB watt equals how many dB milliwatt? Right now you think this one converted into watt equals 1 watt, right? So 1 watt compared to 1 milliwatt, the ratio equals 1,000. 1,000 converted into dB, so this one is supposed to be equals 30, right? So 1,000 converted into dB, take the log base 10, 1,000 equals 3. 3 times 30, so that's equals 3. How about this one? I give you arbitrary. Okay, so P dB watt. Then what is this? This one will be just the plus P. Means dB watt converted into dB milliwatt, you just add the number by 30. That's all. The next one will be dB. What's the next one? Can you guess? dB microwatt. But this one used very frequently, so we will just remove this one. dB micro, that's all. Everybody knows dB micro means dB microwatt. And this one here, dB watt will be equals to 60. If I put 0 here, 0 equals 60 dB micro. We should be able to convert those units back and forth. So quickly. So dB is a unit. dB watt is a power unit. And dB watt can be converted into some power. Okay, any question for this? Why we want to use the dB, this concept? dB can change a multiplication operator into an addition. Sometimes we would like to calculate addition instead of multiplication. For example, if you have a amplifier A1 and A2 here, and we have maybe another one, A3. Suppose the gain here equals 20, the gain here equals 5, the gain here equals 10. So what is the total gain? The total gain, that's easy, right? Because these three are connected in series, so we just multiply all this together. 20 times 5 equals 100, and then times 10 equals 1000. So that is in absolute values. 20 means 20 times larger, 5 means 5 times larger. We are talking about in power. Right? Now, if this given in dB, then you just add all these dB values. Right? I'll give you another example. Suppose this is 10, this is 100, and this one is another 10. Let's try. So again, these are not in dB, it's absolute value. So the total again will be 10 plus this plus this. Multiply this, multiply this. So that will be 10,000. Right? Now we convert this one in dB. How many dB is this? Log 10 base 10 equals 1, then times 10, okay, equals 10 dB. How about this one? 20, okay, so 20 dB, and this one, same, 10 dB. We said in this, use absolute value, we just multiply this equals this. And here we need to add 10 plus 20 plus this one equals 40 dB. Now, is 10K equals 40 dB? 10,000 is equal to 40 dB. So that means we use this one. Sometimes use addition is much easier. For example, if we have attenuator, later time we are going to discuss radio wave propagation. For example, the signals transmitted from a satellite to the Earth. In between, in this link, we are going to have attenuation. For example, because of the rain, because of the atmosphere, all this thing. So the gain will be a number less than 1. That means attenuation. In that case, we should divide by that factor, or we just multiply this. Minus that attenuation. So
what is the 10K in?
10K equals 1,000.
No, I mean like
10,000.
What unit?
Unitless.
It's
This is just a factor. 10 times, 100 times, 10 times. That's the gain. And we connect these three in series. So the total gain, the overall of this system is 10 times 100 times 10. So equals 10,000. That's unitless. Has no unit. The concept is easy, but we should be able to convert back and forth all this unit very quickly. Let's give you another example. Sometimes a guy will go to your home to repair the cable TV, and suppose he has a meter to measure the power level. Now, suppose we do it by ourselves. The power level from the antenna equals, for example, negative, we just made up some numbers, negative 40 dB micro. That's microwatt, right? And we use a branch divider. Divide this one here. You have two TV sets, TV1, TV2. We assume these two are identical. So you connect this one here into here, and you divide this equally. You divide this equally into two. Right. What is the power for the first TV? The input power level equals negative 40. And what is the power here? What is the power here? And we know the power here equals half of this, right?
Negative 20 and negative 20.
Negative 20, negative 20. Everybody agree? Alright, that is not correct. Right? Actually, this one equals negative 43 dB micro. This one equals negative 43 dB micro. Why? Because this power is divided by 2 is the power. The output power equals the input power divided by 2. Right? Now, we are not express this power with the absolute power, microwatt. We instead use dB. So we need to take the log base 10 times 10. Then this one, the same thing, take the log base 10 times 10. Right? So this is the power output in dB. And here, this one is the power in dB here. Now, this 10 plus 10 log base 10 1/2. We know this one equals negative 0.3, then times 10 equals negative 3. So this one actually equals the input power minus 3.
So your PI would be your negative 40 dB?
Yes, this one here is in dB, this one is in dB. Because we multiply, take the log times 10. So this absolute value some watt converted into dB value. Right? So in terms of dB micro, the output power equals the input power minus 3. Actually, you know this number. For example, when you describe the linear amplifier, you said the 3 dB bandwidth. Everybody knows that, right? The 3 dB bandwidth. What does that mean? What does that 3 dB mean?
That's where you get like a linear.
The power from the maximum reduced to negative 3 dB, right? So negative 3 dB, what does that mean? Power reduced to negative 3 dB. That means reduced to half. Right? So the power frequency response like this, right? Yes, we assume the maximum is here. This is 1, scaled to 1. Then 3 dB actually means negative 3 dB. Negative 3 dB is at somewhere here, and this one is half. So you can see negative 3 dB means half. Right? So this bandwidth from here to here is the 3 dB bandwidth. That make sense? Divided by 2 in terms of power means minus 3 in dB. Multiplied by 2 means plus 3. How about if we are talking about the voltage? Suppose you have voltage divider. You voltage divided by 2. What does that mean? The dB, so we still the same dBV, dB volt. That means how many dBs compared to 1 volt. If you use the voltage divider, divide the voltage, input voltage into half. That means dBV of the input must be minus 6, right? Because it's 20 times the log base 10. It's minus 6, right? You just play with a little bit more, then it's not easy to understand. Okay, next we discuss the types of noise. It's very quick. Any communication systems have noise, and basically we have two kinds of noise. The first one is called correlated noise. The next one is uncorrelated noise. There are a lot of methods to classify as noise, but we follow this, right? Correlated noise and uncorrelated noise. Correlated noise means usually from the nonlinear distortion of the circuit. It is inside of the circuit. If you have that circuit, this noise always exists. For example, the first type is a harmonic. You may know this. If you design a circuit, you use this power from here. The frequency equal to 60 Hertz, right? So you may have 120 Hertz noise in your circuit. Sometimes you even have 180. So you need to use a band stop filter, or sometimes we call not filter, to filter out that this input equals 60 Hertz, although you use the rectifier change into DC, but there's still noise inside here. So this is called principal frequency. Then the second is 120, then third, the next one is 180. All these are called harmonics. If you have a nonlinear device, then this harmonics always exist. So this is a harmonic noise. If you have this circuit, this system is working, then this noise always exists. So this is called correlated noise. You cannot remove by, if this circuit system works, then it's always here. You need to figure a way to minimize this. The next one is called intermodulation distortions. Intermodulation distortions means if you transmit 0, 1, 0, 1 here, and sometimes if your power is large enough, power is too large, then between all these power levels, there will be some like distortions. That means for digital transmission, you cannot let the power. We do not see the larger, the better in terms of power. Whereas before, I have in 2005 my cable, the first one in my community with the cable. Okay, at the beginning it's good. Later time it's okay, not working. This you can see the quality is very bad. The technician came and they said, okay, your power level is too large. So how come? Okay, they said because I'm the first one. They expect there are more customers, so that's why they make the power is a little bit larger at the beginning. So if more customers use that, the power level will reduce. But unfortunately, at that time, I'm the only one who uses that. So the power is too large. That means there's some distortions. If you use a digital transmission, at that time maybe not digital, but anyway, the power is too large may not be not necessarily a good thing. Right? So there's a lot of intermodulation distortions. Uncorrelated noise is very easy to understand. For example, we are communicating here, then okay, this is noise from external man-made noise or atmospheric noise or this. So we do not discuss a lot of details here. Next one is called crosstalk. If we have a communication system like this, this is transmit, so that is T and R, transmit and receive, and this one here is T and R, and this one, suppose this one is only R, receive. At this receiver here, the signal may leak from this side. This is called the near end crosstalk, because this is at the transmitter side. The signal transmitted here to this way may leak to this way also. This is called the far end crosstalk. So both are not what we want. Both are noise. How to minimize this crosstalk? We can use better cables. That's easy. Choose quality cables, and we can use a common mode amplifier. Anyone knows this concept? If you take a 312, when we design linear amplifiers, we have a common mode amplifier and we have differential mode. The gain is common mode gain and differential mode gain. So we don't discuss the details here, but common mode works in this situation. And balance the transformers and strength limitation. Just last I said, it do not make the power too large. Strength limitation, and also strength limitation will avoid the over modulation. So we need to consider all this. Alright, next we discuss. We have all these type of noise, but we are going to discuss in detail only one. It's called thermal noise. Thermal noise. Any communication system is working with a bandwidth and working in a temperature. So what is the thermal noise and what is the power of the thermal noise? The thermal noise power is represented by N equals K times T times B. K is Boltzmann constant. That is called Boltzmann constant. And this constant equals 1.38 times 10 to the negative 23 joules per K. K is the temperature here, absolute temperature in unit of Kelvin, not in Fahrenheit, not in Celsius, it's Kelvin. How to convert this temperature? For example, this room temperature maybe equals 20, suppose equals 25 degrees Celsius. What is this temperature in Kelvin? Plus 273, right? Point something, but ignore that. So every time you use the Celsius temperature, then plus 223, so this one we are converting into this one. So don't use this one, don't use the Fahrenheit, right? We have mistakes before this. So
Is this under correlated noise? Where's the same?
Yeah, this is just thermal noise. It's correlated.
Okay.
Because if you have system, you always have this thermal noise.
Yeah.
This one here, T is temperature in Kelvin, and B is the bandwidth. B is the bandwidth in Hertz. Okay? So we multiply all these three, then we get the power, the noise power. So this is called the noise power. Now let's approximate how large is this noise power. This one equals 1 point something times 10 to the negative 3 joules per K. And this T equals like, for example, in room temperature like 300. Right? So we multiply this one by 300. And this bandwidth, what is the bandwidth of your cell phone or anything? Right? Like 10 meg, for example. Right? AM radio is like several tens of K, several dozen of K. FM is like 200 meg or something. Right? So we just make some assumptions. So suppose B equals 10 meg. Right? We just make some sums. Okay, now let's multiply all this together. So this is 1.3 times 3 here, so that equals 4. 4 times this one is negative 23. This one is plus 2. This one is 7. Right? Make sense? So this one, the power equals this one 7, so it equals 4 times 10 to the negative 16 joules. Then this is the power. And this power definitely is too small, right? So every time if you have an amplifier, you say, okay, this is noise power, but your input power usually is much, much larger than this one. So you think, okay, we can ignore this. Right? So that means this number is too small compared to the others, and it's not convenient to use. Instead, we just put this number here. For example, it equals 4 times 10 to the negative 16. Right? So sometimes we have another concept, it's called noise voltage. Instead of representing this noise power with this, we represent that noise with a voltage. So what does that mean? It means, for example, if we have a system here, and we have internal resistance, and we have a load, right? And the thermal power is applied to the load. We know that, right? Now, I consider equivalently, instead of the power here, we have some noise voltage here. It is this noise voltage that applied to the load, the noise power. So this power here gives us the power as this one here. But I just consider there's some noise voltage here as the source applied to our system this power. So this power is the same, but it is from a noise voltage. I want to know how large is this voltage. Does it make sense? Okay, now recall in 101, the maximum power transmission. If we have a source, this source has a, okay, we put this one in here. This is the internal resistance. That is the load. When does this load take the maximum power transmitted from the source? It's the maximum power transmission rule. It is when this load equals this small r. When these two are equal, then maximum power will be transmitted to this load from this source. At that time, that means this big R equals this small r, so both are equal to this R. At that time, the voltage on here, on the internal resistance, will be equal to the voltage here. So this voltage actually equals, because this voltage here is Vn, noise voltage, so this is Vn over 2. And we know this here, V squared over R, and this is the power dissipated in this load. And we let this this power here equals this N, which is KTB. So KTB, the noise power. Now we just want to find out what this thing is. It's noise voltage. That's very easy to find. So VA from here equals KTB times R. Then take the square root, then times 2. So that is just 4 like this. Now we use this as an example here. We know KTB is like 10 times 10 to the negative 16. And the R is the input resistance of the communication system. For example, we just use suppose we use 10K. Right? We just made up some numbers. Anyway, that's the resistance. So this one will be times 10K, means 4 here. Then times another 4 here. And then take the square root. This gives us the noise voltage. And take the root, so this one equals 4. And this one is negative 12. Then take the square root, so that's negative 6, right? So this noise voltage equals 4 times negative 6. The unit equals volt. So that is like a 4 microvolt. That number is reasonable, right? This number is not as small. For example, if you use small signal amplifiers, that input signal is small, it's millivolt or something. This is comparable. So we can just add this noise to our input, then do some analysis. Instead of this extremely small power, we prefer to use this noise voltage. Now you can see the noise voltage actually is also depends on the impedance of the system. Any questions on this? Okay. We know we have a lot of noise in the communication system, but to calculate, to make the class simple, we only consider the thermal noise in this class. Now we know we have a signal and we have a noise, so we are going to use this ratio called the signal to noise ratio. Signal to noise ratio equals the signal power, the power of the signal, and we use a P to make sure this is clear. So the power of the signal then divided by the power of noise. In here, this noise, power of noise is just N. So just the power of the signal divided by the power of the noise. We call this one as the signal to noise ratio. S and R, or sometimes we just use S over N. You are going to see both representations in reference online or any other books. S over N or S and R is defined by the ratio of the parts. So for example, if your input equals 1 watt, if your noise power N equals in our example here equals 4 times 10 to the negative 16. That was okay. 4 times negative 16. And this one here, you multiply it. Suppose we just use 1, makes things easier. So the signal to noise ratio will be equals 1 over this, so equals 10. Next, this is large. So this is the signal to noise ratio. Because the signal equals 1, the noise equals 1 times 10 to the negative 6. We don't use this for make this easier to calculate. So the ratio equals 10 to the 6. So we see this signal to noise ratio usually is very large. Then we know dB concept. So we would like to convert this one into dB. Because we are talking about the power here, so we need to take the log base 10 then times 10 or 20? 10. Okay. So this one will be equals how many dB is this? Take the log base 10, so because this is already a power of 10, so that is only 16. Then times 10, so equals 160. 160, what's the unit? dB. Not dB watt, because this one is the ratio. Unit is, so 160 dB. We prefer to deal with this number. 160 is good, but we don't like this big number. So that's another purpose to adopt this dB concept. The numbers is reasonable. For example, if this was this one, 10 to the negative 16, how many dB is this? Negative 160 dB, right? This is better than this smaller number. So make the numbers are more reasonable. Okay, now we know the concept of the signal to noise ratio. We consider a real, more practical communication system. So this one here, communication system, make this very simple. And suppose this is just the amplifier. Right? And for at the input side, we have a signal to noise ratio at the input. And this one has a gain of A. That means any input is multiplied by A as the output. And we have a additive noise inside here, and that is the thermal noise. The thermal noise I just use as N as here to represent. This is called additive. Additive noise means this power will be just added to this, not multiplied. Right? And we have then at the outside we are going to have a signal to noise ratio at the output. We want to derive the relationship between these two signal to noise ratios, the input and the output. The signal power at the output equals the signal at the input multiplied by A. Because this is just a linear amplifier. And the noise at the output equals the gain times the input noise and plus this additive thermal noise. Now, what is the signal to noise ratio at the output? That one equals the signal at the output divided by the noise at the output. So that means this one equals ASI over ANI plus additive noise here. We just calculated the signal to noise ratio at the output, which by definition is the signal divided by the noise. And recall that the signal to noise ratio at the input, that equals the input signal divided by input noise. Right? We combine these two together, we do some math, and we try to find the ratio. The ratio is defined by the signal to noise ratio at the input divided by the signal to noise ratio at the output, and we call this one as a factor F. That's the definition here. The input signal to noise ratio divided by the output signal to noise ratio. Then this one here, this one is here. So we use this, and we find that this ratio equals 1 plus R over A, N over NI. And we call this as a noise factor. Noise factor, so that's F here, right? This F is noise factor. Definition is the input signal to noise ratio divided by the output signal to noise ratio. Okay, now let's comment this formula, the noise factor. Is this larger than 1, less than 1, or equal to 1? Look at this. This is the power of the noise, positive, right? Power of the input noise, positive. Gain, positive. So this one should be bigger than 1. Eh? So that means bigger than 1 means the signal to noise ratio at the input is always bigger than the signal to noise ratio at the output. That means you can only make things worse. Your signal to noise ratio can only reduce after this amplifier. Does that make sense? because this noise factor is greater than 1. How to make this one equal to 1 or as close to 1 as possible? Look at this. This is constant here. We can do nothing. We make this gain as large as possible, equals infinity. Then this part are close to 0, so this one is very close to 1. That is one thing, right? Another thing is you make this thermal noise equal to 0, then this part equals 0, so it equals 1. Thermal noise equal to 0. Thermal noise, K constant, nothing, T, B. You make the B equal to 0, that means no bandwidth. Then why you want that system? No bandwidth. We can do nothing. So this one must be here. The only thing we can make T equal to 0. How to make T equal to 0? You reduce the temperature of this thing, okay, up to absolute 0, and put this in liquid nitrogen or even lower outer space. Right? At least make this one as small as possible. In that case, this thermal noise is very small. So all the input power and all input noise will be amplified by the same ratio, so the signal quality will not change, keep the same. Right? Or you can make the gain as large as possible. The gain as large as possible. Any question on that? Although we give you this formula to calculate the noise factor, but I do not suggest you to use this one because I don't want you to memorize a lot of things. You only need to memorize the fundamentals. So what is the definition for this? The input signal to noise ratio divided by the output signal to noise ratio. How to calculate the signal to noise ratio? The signal power divided by the noise power. Right? Then you just calculate this from the definition. And we are going to use an example to show you how to do this instead of using directly this formula. The next one is, this one only works for one stage. Right? How about if we have for example, if we have two stages, we have here 1 and we have 2, we may have more. So A1, that's the first amplification factor, A2, and we have O. What is the noise factor from the couplet system? Again, we can derive just like this, but I don't want to waste your time. And the total, the overall, and the total noise factor will be equal to F1, which is the noise factor of the first stage, then plus F2 minus 1, F2 is here for this, then divided by A1, A1 is the gain from here, then plus F3 minus 1 over A1 times A2, and so on. If we have next one is F4 minus 1 over A1, A2, A3, and so on. This A1 is here, this A1, A2 is here, and this A3 is here, and this F4 is here, this one here, this one is here, this one. Now you see this total, the total noise factor depends which part contributes the most. F1, right? Because F1 just F1 copy here. How about F2? Okay, F2, the contribution from the second stage, the first one you need minus 1. Minus 1, look at here. If you minus 1, that means this one is gone. We only have this one. Hopefully this one will be small, right, compared to 1. And that is our wish. So this one is smaller, but also you divide it by A1. What is A1? The gain of this stage. For example, if your gain equals 10, then this one is reduced by 10 times. So this one is smaller compared to this, hopefully, right? How about this one? This one is even smaller. Why? Again, minus 1 here, smaller, but also divided by A1 times A2. So if this one equals 10, this one equals 20, then this product equals 200. Right? After the minus 1, then you divide by 200, this number is even smaller. Then we can expect this one is, must be even smaller. So the largest contribution is from here. And now look at this formula. What can we get from this formula? For example, when you design a system, before you already designed the linear amplifiers. For a system, the first stage is a pre-amplifier, right? What's the purpose for the pre-amplifier? Well, first thing is, for example, impedance matching, right? We don't discuss that. We discuss in terms of noise, right? Usually, you are going to use your best quality device in the pre-amplifier. For example, the low noise, the resistance or inductance or this IC chips. Why you want to use that? Put your investment in the first stage. The gain not necessarily large. We can use the gain equals 1 or very small, but that doesn't matter. That's not the purpose for the pre-amplifier. The pre-amplifier is to reduce the noise factor of the whole system. If your quality here is good, that means this F1 is small. Then all others, like worse and worse qualities, will be followed here. Then divided by this gain, so this -1 divided by this gain, so it's small. So you put your best thing at the very front, and to reduce the overall noise factor of the system. So that is the second purpose. Right? We know that when we design a linear amplifier, how about you implement, for example, a communication system? You have a transmitter, you have all these things together, right? In this class, you want to put your best system at the front. Right? Then second, then next. So when you implement the system, you also follow these rules. Okay? Next one, we are going to discuss example how to calculate the thermal noise. The example here is we just see on the slide, right? I'm write some numbers in simple way. The input power Pi equals 100 watt microwatt. So that's small. Microwatt. The input noise Ni equals 1 microwatt, and the gain equals 20 dB, and the additive noise N equals 100 microwatt. You can see this one, additive noise is large. Right? So it's not very good system. And what we want is find the noise figure. Right? What is the noise figure? What is this? Okay, noise figure. We know noise factor here. Then noise factor converted into dB give us noise figure. Right? So we write here noise figure is just 10, because we are talking about the power, right? 10 log F. Yeah. Once you find the noise factor, then we just convert it into dB, so that's it, noise figure. Alright, now solution is everything is given here, then you can use this formula, but as I said, you don't use this. Instead, we calculate the signal to noise ratio of the input equals what? Input power divided by the input noise. So that's equals Pi over Ni, then equals 100 divided by 1, so equals 100. Keep in mind here we use all use absolute numbers, not the dB value. Right? So that's equals 100. Then what is the signal to noise ratio at the output? The output equals the output power divided by the output noise. Output power equals the input power times A times the gain, right? So this one equals 100 times the gain times 20. No, right? We need to convert this one to the factor. So times what? 20 dB equals what? 100, right? Because we are talking about power. So times 100. So that is the input signal. Right? How about the input noise? Output signal. Output signal power. Output noise power equals the input noise, which equals 1 times the gain. Again, equals 100, not 20 dB. Keep in mind, don't use 20 dB. Then plus the additive noise, which is 100. So on the top, that will be equals 100 times 100. This one equals 200, so that one equals 50, right?
So you said the additive noise.
Just the additive noise.
Where'd you get that?
This is given here.
Okay.
This is as an additive
And
noise.
you didn't use the microwave because they're all.
No, this one just add to it. Do not. So here, this is the gain. This is the gain. This is the input. This input is multiplied by this A.
Yeah.
But the additive noise here, just add to it. Won't pass. This is the gain. Just add to it.
I'm just saying you didn't put the units on it. It's like.
Yeah, everything is. This one is unitless. This is 100 micro. All the power are.
Yeah,
All the units are.
Yeah, they're all micro.
So all micro. So I just ignore the micro. Okay? You can write the unit, but in this case, it's good because all the units are the same. If it's not the same, for example, I said okay, 100 something, then you need to convert the. Just make sure. Yeah, that's good. All right, equals 50. This ratio, right? Signal to noise ratio. Signal to noise ratio at the input equals 100. Now after the system getting worse, it's 50. Right? So what is the F?
22.
All right. We just plug this in the definition, right? So 0, so equals 100 over 50, so equals 2. So the noise factor equals 2. We are looking for is noise figure. So noise figure, we said NF, right? Noise figure is NF. Noise figure, so NF, what is this? NF equals, it converts 10 log base 10 F. Log 2 base 10 equals 0.3, then times this one, so that's equals 3 dB. Right? Question on that? Good, right?
So is 10, is that noise factor
10.
or noise figure?
Which 10?
NF.
This one?
That's the
Yes. Is that noise figure?
This one is noise.
Okay.
This is noise factor.
Okay.
Noise factor is the ratio of the signal to noise ratio. Then you convert this one into dB, that is called noise figure. Noise figure is some dB. Noise factor is just a factor, the unitless. We discuss some other concept in information theory. So information capacity. The primary communication resources are the power, the transmitted power, and the bandwidth. When you use the internet, you want a wider bandwidth, and you want a strong signal. All this transmitted signal is very precious. So if they increase the transmitting power, then the investment will be large. For example, if we double the transmitting power, then the cost will be more than double that. So that's why the companies usually they want to reduce the transmitted power and use only as necessary, not more than enough. For example, in mobile communications, wireless communications, they can use one transmitted power to supply, for example, to the whole city. For example, this one equals 100 watt. We just make some numbers. Or they can make some small ones. Use 10 small ones. Each one is 10 watt. This is called a cell phone, right? Cellular system. So each one, this one here, in this system, so they have 10. So each one is smaller. But the cost for this 10 smaller ones will be less than the cost for the one big ones. That's why they want to distribute this. But anyway, the transmitted power is a primary resources and bandwidth. If we know the power in terms of signal to noise ratio, and if we know the bandwidth, if we know these both two factors, what is the transmission capacity? That means how fast we can transmit. Right? From information theory, this is called Shannon's equation. Shannon's equation gives us the channel capacity. This means how many bits can be transmitted in each second. And will be proportional to the bandwidth. The larger the bandwidth, the larger the capacity. Then it is related to signal to noise ratio. The larger the signal to noise ratio, the larger the capacity. And this one will be added to a 1. Usually we know the signal to noise ratio is very large, right? It's very large, so this add 1 just can be ignored. And this one here, then we take the log base 2 here. So that is Shannon's equation of capacity. Now look at this, because we are taking log here, this one cannot be dB. Keep in mind, this one is not dB. You need to use the absolute value. And because we are going to take the log here. You cannot take a log of the dB, right? Alright, let's find some real examples. For example, your cell phone, the signal to noise ratio. Anyone knows what's the signal to noise ratio of your cell phone? Digital cell phones, maybe 40 dBs and 50 dBs. 50 dBs is too much. 40 dB is reasonable. Okay, can be as low as 20 something. It's even lower than you cannot use it. So we just make. So for example, this one equals 40 dB. Suppose it's 40 dB, and the bandwidth. I don't exactly know what the bandwidth of cell phone, but we consider a communication system. Suppose equals 10 meg. Just made some numbers bandwidth. Okay, now we know these two factors. What is the capacity? That means how many bits can we transmit in each second. All right, let's calculate this. Here, this one here equals B equals 10 to the 7, right? 10 meg. Then times log base 2, 40 dB equals, as we said, we cannot use 40. We need to use 10,000, right? Okay, we need to use 10,000. 10,000 plus 1. We don't need to care the 1, okay? We just use 10,000. Okay, how large is this one? Okay, approximately equals what? So let's see, 2 to the 10 equals 1,000, right? 1,024. Make sense? 2 to the 10 equals 1,024, right? And 2 to the 13 times 8, so that's 80,096. So very close to 10. So that means this one almost equals 13 something. This part, you can use a calculator to do this, but sometimes you need to approximate, right? So this one is close to 13, right? So suppose we use 13, so this 1.3 times 10 to the 8th. That's the right? That means that equals 130 megabyte per second, PS. In each second, we can transmit 130 megabytes. This is the capacity. Doesn't mean you can really transmit this. This is the maximum you can do it. There are a lot of other factors that will affect this transmission rate. But this is the maximum. You cannot exceed this. The last concept we are going to discuss is called the bit error rate. It's very simple. Bit error rate. Bit error rate. That's easy to understand. You transmit some number of bits, and at the receiver, some will be received mystically. So that's called error. Total transmitted. Then you just use this number. number that received mystically divided by the total bit transmitted. That is called bit error rate. For example, you transmit 1 million bits, but you received 10 bits wrong. I transmit 0, you receive it as 1. I transmit 1, but you said that is 0. You receive 0 because all these factors in the communication link, right? You have mistake. So what is the bit error rate? This is the total. I total transmitted 1 million bit, but you receive this 10-bit error. So the bit error rate will be this one over this. Right? So 10 over this. So that's give us a 10 to the negative 5. That is bit error rate. Right? Bit error rate, that's easy to concept. You just use the total number of mistake then divided by total number transmitted. We have homework to practice this. Factors that contribute to the contributing to bit error rate. What do you think? What factors will contribute to bit error rate?
Maybe distance.
Distance, okay. Bandwidth. If your bandwidth is small, you want a wide bandwidth, right? Why? Okay, one reason is you want the error small. Right? If the bandwidth is small, then bit error rate will be large. The signal to noise ratio. The larger the signal to noise ratio, the smaller the bit error rate. If your signal is too low or your noise is too large, definitely you are going to have more errors. Transmitted speed. Sometimes, if your signal to noise ratio is small, you want to reduce your transmission speed. In that way, the error will be smaller. The faster you transmit, the more the error. And transmission medium in between. You want to make a call in the sunny day. Right? You don't want to make a call in the thunderstorm because the signal will be worse. Sometimes you may not make a call. For example, in the thunderstorms, in the desert area, the dust, all dust, sand, storm, then sometimes the communication system just won't work. Transmission distance, as you mentioned, the longer the distance, the more probability you have bit error rate. Transmitter and the receiver performance, you want to have better quality. Transmitter and the receiver both. So that's easy to understand. Okay, the last concept is called noise power density. Look at the noise power we discussed here. Noise power equals KTB. So that means the larger the bandwidth, the larger the power noise, the power of the noise. We always want a wider bandwidth, but that means the power of the noise is also large. So that's look like we don't want this, but we want this. So that means there's something like in here. We may have better concept. That is called noise power density. Noise power density is just we use N0 to represent, and that is just K times T. Just the noise power per bandwidth is divided by bandwidth, and that's only this. So you can see this is only proportional to the temperature. The next concept is important here, and we just mentioned this, is EB per N noise power density. EB is the signal energy per bit, energy per bit. This ratio to the noise power density. And if we know the transmission rate, if we know the noise, the signal power, we can easily calculate this. So this one will be equals S times TB. TB is the time duration per bit. Signal power, this, then divided by N0. And I'll plug into numbers. That one equals N0R, or equals SKTR. So this signal energy per bit to noise power density equals signal power divided by K, Boltzmann constant, temperature, and the transmission rate. So this is related to this. And the bit error rate is a function of this, and we are going to discuss this in the following chapters. We know this one does not depend on the bandwidth. The bandwidth is here, but after this one divided by the bandwidth, it's not a function of bandwidth anymore. Okay?